Hey everyone, and welcome back to The Explainer. I am so excited to guide you through today's topic because we're essentially going to look at a high-stakes investigative procedural. But instead of a traditional crime scene, our subject is the Earth itself. We're going to uncover the hidden science that happens long before a shovel ever hits the dirt on a major development project. Okay, let's dive into this, because it's a massive question, right? When a corporation proposes a colossal new infrastructure project, say a huge new steel plant or a really deep open pit mine, how do we actually know the Earth can handle it? How do we know a new mega mine isn't going to swallow a nearby village, or that coring a massive foundation won't inadvertently drain the local aquifer that farmers rely on? The real-world stakes for environmental impact assessments, or EIAs, are incredibly high. So to answer those life and death questions, we need a very specific kind of expert. Enter our protagonist for this explainer, the functional area expert, or FAE, specializing in geology. Armed with a clipboard, field logbooks, and just a deep understanding of the planet's mechanics, the geology FAE acts as a specialized investigator. Their whole job is to rigorously evaluate the geological, geomorphological, and geotechnical characteristics of a project site. They have to guarantee that these developmental activities are actually safe and environmentally sustainable. Think of our agenda today as the official case file docket. We're going to quickly run through 1. The bedrock of EIA, 2. Gathering baseline geological data, 3. Geotechnical and hydrogeological tests, 4. Predicting environmental impacts, 5. Geohazards and mining risks, and finally, 6. QMS and data integrity. Let's go ahead and open the case file right at the beginning with Section 1, the bedrock of EIA. This is where the investigation starts. The FAE relies on a seriously rigorous investigative checklist. First, they map out the regional and local geology, identifying the overarching geological provinces and major rock types, whether it's igneous, sedimentary, or metamorphic. Then, they zoom in a bit closer to analyze geomorphology and drainage. Finally, they get extremely granular, assessing geotechnical parameters. It's a really fascinating shift in scale. They go all the way from analyzing giant tectonic plates in stratigraphic successions right down to examining microscopic soil porosity. All right, moving into Section 2, gathering baseline geological data. This is where the macro scene is set, and our expert puts boots on the ground. Out in the field, the FAE meticulously documents structural trends in the rock. They're out there measuring the strike and dip and mapping out folds, faults, and joints while analyzing their spacing and orientation. Finding these structural features is honestly exactly like a doctor looking for pre-existing fractures in a patient's bones before clearing them for a heavy lifting competition. If there's an active fault line with historical displacement hiding right under the site, the FAE is absolutely going to find it. And alongside the rocks, they're evaluating the shake of the land itself. Geomorphology maps out the landforms, figuring out if a site sits on a plateau, an alluvial plain, or maybe a denudational hill. Plus, they study the drainage patterns. Is the drainage dendritic, spreading out like tree branches, or is it more of a trellis pattern? By analyzing the drainage density and slope categories, from flat plains all the way up to steep escarpments, the FAA can precisely tell us where water naturally wants to go and exactly how the new project might disrupt that flow. Which brings us to Section 3, Geotechnical and Hydrogeological Tests. We have looked at the surface. Now we have to test the Earth's absolute limits. Now, what's really interesting about these specific parameters is how they literally predict if solid rock is going to crumble under the pressure of human engineering. The FAOE measures the unconfined compressive strength to test rock mass strength. They calculate the rock quality designation percentage. They assess the safe bearing capacity to guarantee shallow foundation stability. These aren't just dry numbers on a spreadsheet. They are the actual physical boundaries of what the site can endure safely. Take the number 300, for example. In geotechnical terms, if you're building a massive project like a new steel plant, the FAE knows that those heavy foundations typically require a safe bearing capacity greater than 300 kilonewtons per square meter. If the earth beneath the site can't hit that number, well, the project simply cannot proceed as designed. No way. But it's not just the rock they test, it's the invisible water beneath it too. The FAE runs through a super strict hydrogeology checklist. They document if the local aquifers are unconfined or confined, and what material they're made of, like alluvium or fractured rock. They're measuring water table depths both pre- and post-monsoon. Knowing these exact aquifer characteristics, along with transmissivity and groundwater flow direction, is exactly what prevents a new development from accidentally draining a local community's vital water supply. Let's shift gears to Section 4, Predicting Environmental Impacts, because gathering evidence is really only half the job. And this brilliantly illustrates the core cause and effect purpose of an EIA. The FAE takes the baseline condition, let's say the natural groundwater table depth, and contrasts it with a predicted change that's going to be caused by the project. If a deep mine requires dewatering, the FAE models the potential drawdown. They predict exactly how many meters the water table is going to drop, and more importantly, who or what that drop will ultimately affect. But what happens when the Earth pushes back? That takes us to Section 5. Geohazards and mining risks. 5 kilometers. That is the critical danger zone radius that the FAE rigorously checks. They scan a 5-kilometer radius around the site for active surface fault ruptures that could trigger devastating earthquakes. If it's a coastal project, they evaluate that exact same 5-kilometer zone for tsunami vulnerability. They're also checking the seismic zonation map of India to see if the site sits in a high-risk zone, constantly scanning for threats like landslides, expansive soils, or soil liquefaction. Once those impacts and hazards are fully predicted, the FAE essentially becomes a doctor prescribing a cure. They recommend very specific mitigation interventions. If slope stability is compromised, they'll prescribe retaining walls. For mining operations, they might dictate controlled blasting to limit vibration or require stowing to prevent the land from literally caving in on itself, which is known as subsidence. And to prevent heavy metals from leaching into the soil, they ensure all hazardous waste storage is rigorously lined. Let's bring it home with Section 6, QMS and data integrity, because honestly, none of this data matters if it isn't completely airtight. The rules here are totally uncompromising. The FAE cannot just use any random test tube to generate their data. The laboratories analyzing soil and water for baseline data absolutely must be officially recognized. We're talking NABET accredited or recognized by the Ministry of Environment, Forest, and Climate Change. Without these certified labs backing it up, the baseline environmental data simply wouldn't hold up in the court of scientific scrutiny. And that ties right into establishing a quality management system, usually based on ISO 9001 standards. I really want to be clear about this. QMS is not just bureaucratic red tape. It is the absolute backbone of a credible environmental impact assessment. It creates this culture of doing things right the very first time, guaranteeing that the methodologies used to collect all that primary data are sound and scientifically valid. Every single step the FAE takes leaves a verifiable audit trail. They use standardized field formats. The experts have to maintain physical field logbooks recording their on-site observations. Any secondary data they bring in must be cross-validated right there at the site. The entire process is subject to internal and external audits. So the crucial point here is that this meticulous paper trail guarantees absolutely no corners are cut when it comes to predicting impacts and protecting the environment. It really is a massive, complex responsibility. The geology functional area expert is out there in the elements, mapping structural trends, predicting aquifer drawdowns, and establishing unshakable audit trails, all to ensure that development doesn't come at the cost of our planet's safety. Next time you pass a massive new construction site or a deep quarry, I hope you'll look at the ground just a little bit differently and wonder what secrets the earth beneath it revealed to the Geology FAE. Thanks so much for joining me on this explainer, and I'll see you on the next one.